China is building a giant laser facility to generate near-limitless clean energy, potentially surpassing the United States in the race for nuclear fusion. Satellite images reveal a massive X-shaped complex under construction near Mianyang in Sichuan province, identified by analysts as a laser fusion research facility. This facility, estimated to be 50% larger than the National Ignition Facility, or NIF, in California, will utilize lasers to create extreme conditions mimicking the center of stars or nuclear weapons, enabling scientists to study materials under these intense pressures. The process involves firing powerful lasers at a target chamber containing hydrogen isotopes, fusing them together to release a burst of energy, a process known as ignition. Nuclear fusion offers the promise of abundant, clean energy without the long-lived radioactive waste associated with current nuclear fission technology. While the United States achieved a significant breakthrough in 2022 with a net energy gain from a fusion reaction at NIF, China's ambitious project signals its determination to take the lead in this field. Experts suggest that the larger scale of the Chinese facility could allow for higher pressures and more material to be compressed, potentially increasing the energy yield from fusion experiments. However, achieving a successful fusion reaction remains incredibly challenging, even with a massive laser. Beyond its potential for clean energy, the facility also raises concerns about its implications for nuclear weapons research. Laser fusion facilities can simulate the conditions of a nuclear explosion, allowing for the development and refinement of nuclear weapons designs without actual testing. Teleportation has been achieved between quantum computers for the first time, marking a milestone in the development of scalable quantum technology. This groundbreaking experiment, conducted at Oxford University, successfully distributed critical units of a quantum processor across two separate computers, demonstrating the feasibility of creating a distributed quantum network without compromising performance. The teleportation, though occurring over a mere 2-meter distance within a laboratory setting, suggests that quantum states can be effectively transferred across an internet of interconnected systems. This breakthrough leverages the unique principles of quantum mechanics, particularly entanglement, where particles become inextricably linked, sharing a correlated fate regardless of the distance separating them. By manipulating these entangled states and performing specific measurements on one particle, the quantum information can be instantaneously transferred to another, effectively recreating the original particle's quantum state at a remote location. This process is perfectly suited for transmitting the delicate quantum information necessary for computations in a quantum processor. In the Oxford experiment, the teleported spin state achieved an 86% fidelity with the original, proving sufficient for implementing a simple Grover's algorithm with a 71% success rate across the two processors. The ability to restructure quantum networks could lead to the development of specialized tools for measuring and testing the most basic principles of the universe, offering insights that were previously unattainable. A new battery can convert nuclear waste into usable energy, offering a promising solution for managing radioactive byproducts. Researchers at The Ohio State University have created a prototype that uses a combination of materials to transform the radiation from nuclear waste into electricity. This battery is designed to power small electronic devices and offers a way to utilize waste that is otherwise difficult to dispose of. While the current prototype produces a small amount of power, the researchers believe that the technology can be scaled up for more significant applications. The battery is intended for use in environments where nuclear waste is generated, such as storage facilities or in specialized systems for space or deep-sea exploration, rather than for everyday consumer use. The battery itself is safe to handle, as it does not contain radioactive materials. The researchers found that the materials used in the battery can be optimized to increase its power output. These batteries offer the advantage of long-term operation without routine maintenance, particularly in high radiation environments. However, scaling up the technology will require cost-effective manufacturing processes. Further research is needed to assess the battery's longevity and limitations in practical applications. The quest to develop efficient and long-lasting nuclear batteries has been ongoing for decades, driven by the need for reliable power sources in challenging environments such as space exploration, deep-sea operations, and remote sensing.